Alright, CNT125. We're looking to review some design concepts or concepts we learned along the way this semester to help us with design if we're designing a network. So let's take a look at some of the different things we've talked about over the semester. First is if we think about the standards for Ethernet, IEEE 8023 or ANSI 568, both of these call for star topology. So as we're hooking up our Ethernet network, we should be thinking star topology, not maybe some own little creation that we have in mind. That's what the standards call for. That's what we should be trying to do when we're hooking things up. Along those same lines, these might be things that are in your fuzzy past, but as we start connecting our devices together, switches and routers and that sort of thing, we should keep in mind some different backbone types. They all have their own pros and cons. Let's take a look at this first one here. This is a serial backbone, or what you could call daisy chain backbone, where you're literally connecting the switches together, kind of switch to switch to switch. First off, if I take a look at this, this is kind of simulating a multi-floor building, very much like where our labs are, our networking labs at the Midtown building, first floor, second floor, third floor kind of deal. I could connect my switches together on my different floors by literally just going from switch to switch to switch. If I look at that, everything's connected. Everything has a path out to the ISP or outside of the network, so it does work. The advantage of this is it is very, I should say very simple to connect up. You're using very limited amount of resources here, cabling and so forth, including very limited ports, a number of ports on your switches. So it gets the job done, very simple, very easy, limited resources. Downside is you look at it, you have some single points of failure. If this link here fails, this whole floor is done. If this link here fails, these two floors are done. If this link fails, all three floors are done. Secondly, all the traffic for this second and third floor has to plow through this switch to get out to ISP, if you will. So bottlenecks, very, very large amount of bottlenecks in this type of network. Moving on to next style, this would be distributed backbone. So in this case, we're going to put instead of just connecting all the switches together, let's put something layer 3 on each floor. In this case, we're doing a router. Now the router network acts as the backbone connecting all the floors together. So right off the bat, I can see that even just this extra link right here, I have some kind of redundancy built in. So if this link up here fails, this traffic still has another path down here and out. So we have a little bit of more redundancy, a little bit more, if you look at the fact that there's a router on each floor, a little bit of more intelligence on each floor, so we could actually start writing some policies of yes, this traffic can, no, this traffic cannot. So we have a little bit more intelligence in our backbone, controlling what is moving across the backbone. Downside of this is we're obviously adding, in this case, 2 more routers to our network. So more cost, financial cost, dollars and cents cost. Secondly, because routers take just a fraction of a second longer to process data than a switch, we are adding cost for latency, time for data to get processed and move from floor to floor. So this is adding a latency cost to our network as well. So there's your distributed backbone. Next style is our collapsed backbone. This is probably one of the more common ways that a building like we sit in is hooked up. All the layer 2 switches out here on each floor are brought together to a layer 3 switch here and then out to the ISP. And the idea of this is this has a lot of switch ports and a lot of high port count. The router down here does not, as you know from working with our routers. So this switch here has a high port count, so it could handle many floors, or in case there's 3 or 4 switches on each floor. 3 or 4 switches on each floor, 4 times 3 is 12. We only need 12 ports here. Okay, let's double up our links and do 2 links to each floor. Now we're up to 24. We still have room in here because this could be a 24 or 48 port layer 3 switch. So this has a lot of port count to be able to handle many switches and or dual links to switches for redundancy. So the pro in this is just that. We have a high port count, very easy. Each link is attached to this guy in his individual link. So if this link fails, it's only affecting that floor. It's easy to add to. If we build another floor and another wing on, I can easily add that link into this switch right here, and now we have some layer 3 intelligence with some control of where data is moving from floor to floor. Downside of this is I still do have some single points of failure. If this layer 3 switch fails, the whole building is done. So there is still some single points of failure. This could act like a bottleneck if I'm not careful, because everything has to funnel through here and then out my network as well. So that's a consideration. Last style is a parallel backbone. Parallel backbone might be something you find in a, I'm going to say like a hospital, where the network must work all the time. There is no possibility for it not working, kind of thing. In that case, what you literally have is a series of duplicate equipment here, layer 3 switch, layer 3 or router or firewall kind of thing out to the ISP. You might not have all of these connections here, but you at least have 2 sets of equipment that switches are connecting here to each, and then switches connecting to dual routers to dual ISP connection kind of thing. And the idea there is you're eliminating those single points of failure. So we're taking the collapsed backbone and kind of putting in some redundancy into it. That's what we're doing. So obviously we have some availability, redundancy issues here for the positive. There is always a path. The downside is obviously cost, financial cost, and kind of the administrative cost of setting it up and maintaining it. All right, while we're talking backbone, something else we should remember: if the connections to the desktop are 100 meg, that link that connects the switch up to another switch. Okay, so let me back up here real quick. Okay, let's just look at the simple collapsed backbone. If we're running 100 meg out here to the desktop, this link here that goes from this switch to this switch had better be gigabit. So as I look at, desktop's getting 100 meg, the link from switch to switch had better be a gigabit. Same goes if I'm running gigabit to my desktop computers, that link between the switches had better be a 10 gig. And the idea there is, let me back up here again real quick. All of this traffic here has to go through this port to this switch. So a gigabit out here to these guys, this had better be 10 gig to handle that volume of traffic, kind of being combined together to be sent to that other switch. Moving on to some devices and results of the devices we're using, and we're talking collision domains, broadcast domains kind of thing. Okay, hopefully remember with the collision domain, the idea behind the collision domain is when we went from the old Ethernet bus network with no intelligence into a hub network that acted very much the same. When I added the switch in, the switch adds the intelligence that it tries to get data to one node and only one node. So therefore the result is on that switch, it's actually trying to dedicate bandwidth to each communication, each sending and receiving. As I send data into the switch and it passes it out to the receiving node, it's trying to allocate that full bandwidth to that communication. So the result is, let me go down to our picture here real quick. If I take a look at this side of the network over here, this hub right here, that was your layer 1. As data moves into the hub, it literally sends it out to everybody. So when it's doing that, it's actually sharing that bandwidth because everybody's getting it. Therefore, everybody has to wait for that transmission to be done. Meanwhile, on the switch, as the data gets sent into the switch, it tries to send it out to one and only one node. Well, while that's going on, the same thing can be happening for 2 other nodes. So the switch is actually trying to allocate full bandwidth to each communication session by just sending it to only one node. So therefore, it's creating many small, tiny collision domains, which is a good thing because I'm not sharing bandwidth with anybody anymore. So a switch network like we have over here, each single node, each single thing is a collision domain. It's not, and it's getting full bandwidth. It's not competing with anybody. That is all a good thing. So using switches everywhere, I'm basically creating individual collision domains, which is good, and that means I'm getting full bandwidth to everybody, which is good. That's what we're trying to do. Meanwhile, on the broadcast domain front, if I take a look, I'll go back to this picture here. It's only something layer 3 that can actually create broadcast domains. In other words, something layer 3 is the only thing that'll have enough intelligence to say, no, don't pass that broadcast on. Keep that contained here to this network. So any broadcast that would happen over here on one of these nodes is going to get passed up to the router, and the router's going to say, no, I'm not going to pass that on to another network. So it keeps that traffic contained. And as we know from doing Wiresharking, certain protocols broadcast. It's just what they do, like ARP, for an example. And if I don't contain them, they spill out across the whole network and rob the network of valuable bandwidth, because we're all waiting for that ARP to go by, if you will. So routers are going to stop broadcasts or create little broadcast domains. The other thing it does is our VLANs. Don't forget our VLANs. Which brings us to our next slide. Remember, VLANs, we're creating them on layer 2 switches, and they are there to create these little broadcast domain areas, little areas of like isolation. And those areas, I'm not going to let the broadcasts out, so that traffic gets contained. And this is another way to control broadcasts. It's another way to even implement a little bit of security. Because if you remember, from VLAN to VLAN, you were not pinging between them. So therefore, you're not sending traffic between. So it's a little containment thing. And if you think back to even this example we did in the lab, we created VLANs on one switch. And VLAN 10 and VLAN 20 would not communicate with each other, and that was all done by the VLANs created on the switch. We then created the trunk going between the two switches, 802.1q trunk frame tagging. All the traffic coming through this switch gets tagged as to what VLAN it belongs to. So when it comes to this switch says, oh, okay, I will share that frame out the VLAN 10 ports, but nobody else. So that allowed VLAN 10 up here to talk to VLAN 10 down here because it's frame tagged. And that is creating, if we go back here, areas of broadcast control. That VLAN, that traffic, any broadcast in that VLAN will be contained there and not go anywhere else. And it also creates a type of security too, because VLAN 10 traffic here is not going to mingle with VLAN 20 traffic. So VLAN 10s cannot Wireshark VLAN 20, if you will. That kind of thing. So it's creating a level of security. Also remember, as we did some of our other labs where we implemented the router with the sub-interfaces, the sub-interfaces were there to recognize the VLANs on the switch to allow us to do inter-VLAN routing. And I think I have another one here as an example for you, allowing us to do inter-VLAN routing. So now the router recognizes the VLAN tags, and I could, if I wanted to, have this computer here in VLAN 30 as it is, I think this is an example here, VLAN 50, whatever it is, I could actually have that talk to a computer over in another VLAN if I wanted to, but the traffic is going to go through the router to do so. And the reason behind doing that is when I run the traffic through the router, I can also put on there an access control list that will limit that communication to, oh, you're allowed to communicate via HTTP but nothing else, no Telnet, no SSH, no FTP, any of that sort of thing. So by setting the router up to recognize these VLANs, I can allow inter-VLAN, but I can also put a roadblock in there to say, yes, this can, or no, this cannot, this particular traffic cannot. Don't forget, we've been using virtual machines all semester. These literally could be servers that you're running in various parts of your network. That's one of the reasons we've been using the little the Linux VM to boot it up and work with it, but that also could be a server sitting and working in a certain part of the network. Just like our network management station, if you think back to booting up the Linux VM that had the network management software on it and running. That is very useful. Don't forget, with wireless, your standards and the ranges they're capable of, what distances they're capable of, bandwidths and distances kind of thing. Okay, that would matter as you're trying to engineer in wireless networks, coverage area for wireless networks, that sort of thing. Don't forget that. Don't forget also with your wireless devices and IP phones, power over Ethernet. Your switches should be capable of power over Ethernet to power the IP phones and access points and that sort of thing. Alrighty, I'm going to come back on the next one and continue on. Next podcast and continue on.